This is the first podcast for solutions. In this podcast, I'm going to cover some basic information that you're going to need to know and reference back to during the entire unit. Specifically, we're going to talk about definitions and units of concentration. So let's talk about some basic definitions, words that I'm going to use over and over again that you just need to know as soon as I say them. First of all, let's talk about what actually makes a solution. A solution, anytime you hear the word solution, referring to a homogeneous mixture of two or more substances. Now, hopefully, you remember that the term homogeneous means looks the same throughout. Okay, so we're talking about something where no matter what, no matter where in the solution I'm looking, it's going to have the exact same composition. Inside of that solution, there are two things. You have the solute and the solvent. The solute is the stuff being dissolved. So, for example, let's say I'm going to make a saltwater solution. The salt is being dissolved in the water, so the salt would be considered my solute. My solvent is the stuff doing the dissolving. So it's whatever the solute is being put into. Again, my saltwater solution, I'm talking about water, and that is dissolving the salt, so the water is my solvent. We're going to use water a lot. Water is what is called the universal solvent. So we're going to see water pop up in almost every single example that we do. Okay. Now let's talk about units of concentration. And these are definitions for concentration too. Because this is how these concentrations are defined. And I'm going to show you some examples on how to calculate involving using some of them. So anytime you hear the word concentrate or concentrated, concentration, etc., we're talking about how much solute is dissolved in a given amount of solvent. So if something is concentrated, that means high amounts of solute in our solvent. So, for example, stuff from your real life. You ever see on the side of your orange juice container, it says not from concentrate. In other words, what they didn't do was they didn't take the stuff that comes in the can and dissolve it in water. So when you go to I don't know if you've ever done this, my parents used to do this all the time. They'd buy the frozen orange juice in the can, and then we'd go home, we'd dump it into a pitcher, and then we'd fill the pitcher up with water, and we mix it all up. That was using concentrated orange juice, and then we made it diluted by adding more water. There are two main units of concentration we're going to use. The first one is molarity. Notice the big M. Molarity is found by taking the moles of my solute and dividing by the liters of the solution. This is the most common one for chemistry because as you've seen so far as we're doing chemical reactions, we often will know how big a bottle is and we'll know how much solution is in that bottle, but we don't necessarily know how much water was put in there in the first place. So knowing the total volume is very important to us. Molality is not used as often. We'll use molality a little bit later when we talk about colligative properties, but molality, little m, is found by taking the moles of the solute divided by the kilograms of the solvent. Notice the difference between the two. Okay? So in the case of molarity, you don't need to know how much water you put in. You just need to know what the total volume is when we're done. In molality, you have to know how much water you put in. Now, why do we use molarity versus molality in chemistry more often than not? Mostly because if you think about it, anytime you add solute to water, it's going to go up in volume. So you know that it's going to go up in volume. So if you identify what the total volume is at the end, then you can identify what the molarity of the solution will be. Now, two other units of concentration that we will use, not used as much, but will be used, are mole fraction and mass percent. Mole fraction we talked about when we were talking about gases. Okay, mole fraction, you take the moles of your substance and divide it by the total number of moles. This is not as useful as it is in gases because we talk about gas mixtures, but we talk about a mixture of solutions, this will become useful. And then mass percent, we deal with this one a lot. You see like a 40% by mass solution. They're talking about mass percent here. And to do mass percent, you take the mass of the substance divided by the total mass of the solution. Now, if any of you have parents that are doctors, or work in hospitals, nurses, etc. You may have seen this on like the side of a saline solution container, like one of those saline bags, or some medicine, different types of painkillers, etc. Things that get hung on that little metal rack. They tend to do those things by mass percent or by percent by volume. So they're both the same type of calculation. Mass of the substance divided by total mass of the solution times 100. Now let's do an example. So here's an example of molarity problems. Here's an example involving molarity. 1.75 liters of a 10.7 molar solution of NaOH is made at 20 degrees Celsius. How many grams of NaOH were used to make this solution? First of all, there is always going to be information in this problem that you don't need. You don't need the temperature. Now, why do they give you the temperature? Because solvents can only dissolve solutes at certain temperatures. So when you change the temperature, you're changing how much solute can dissolve. So they always give the temperature so that no one can ever say, oh, well, you didn't give us the temperature, so I can't identify how much can actually dissolve. Yes, they actually say it in that voice too. So again, it's a calculation problem, so the first thing you do is write down your formula. This is molarity. I'm sorry, I'll make it more look like a big M. Molarity, big M, is equal to moles of solute, which in this case is the sodium hydroxide, divided by liters of my solution. They tell me that my molarity is 10.7. They tell me my volume is 1.75. So since I only have three things, I'm going to put in X for my moles. Now, does that help me? Does that answer the question? No. The question says how many grams, but I already know that I can convert from moles to grams, so let me find the number of moles and then do a quick mole conversion. So I'm going to cross multiply, and I'm going to find that X pull out my calculator. So I'm going to cross multiply 10.7 times 1.75 is 18.725 moles of NaOH. So throw that into a quick mole conversion. 1 mole goes on the bottom, 40.01 grams goes on the top. Made that line a little long. Go back to my handy dandy calculator. Number's already there, so I'm just going to go times 40.01. Enter is 749.2. But I need three significant figures, so we'll round it to 749 grams of NaOH. Okay? That's a lot. Just an FYI, to put it in perspective, one of those iodized salt containers that you buy from ShopRite is about 750 grams. So you can tell how much sodium hydroxide you need in this solution. But if you think about it, this is a big solution. 1.75 liters is almost a 2-liter soda bottle. Okay, so that's a lot of solution that you're dealing with, and it's a pretty high concentration, 10.7, very concentrated solution. So I need 749 grams of sodium hydroxide to make this solution. Let's see another one. What is the molarity of a solution formed by mixing 10 grams of H2SO4 with enough water to make 100 milliliters of solution? Okay, so again, write down your formula. Molarity is equal to moles, in this case it's H2SO4, divided by liters of solution. Plug in what you know. Okay, it wants me to find the molarity, big M. I have a volume, but it's in milliliters. I'm going to divide by 1,000, and that will give me 0.100 liters. But I don't have the moles, and I'm looking for molarity. So there's got to be something else that I can use to find the moles. I have grams, so I'm going to quick do a gram conversion. Gram to mole conversion. 1 mole goes on the top. 98.04 grams is the weight of H2SO4. Goes on the bottom. Quick do my calculation. Clear out my previous one. 10 divided by 98.04 is 0.102, which will go on the top over here. And hopefully you'll be able to see the math here already, but I'm going to do the calculation anyway. Divided by 0.1 is 1.02 molarity. Now, notice you must include the m. This is the unit. Okay? Muy importante. If you do not put the m, I'm going to take off points for forgetting your units. So make sure you put the big M in there on the end. Even if you put it up here, you still have to put it in here. I'm telling you now, I'm taking off points if you don't do it. Okay, so pause the video. I'm going to quick solve this one and come back and you double check to make sure you got it correct. So let's go through this and double check right now. Okay, so again, write your formula. Remember that bromine is diatomic, Br2. So it says how many grams are needed. They want a 0.100 molar solution. I'm going to solve for moles because it says grams, and anytime they say grams, that means you're going to have to do a mole conversion. So 0.1 times 0.5, I don't even need a calculator for that to know that it's 0.05, oops, X is equal to 0.05 moles of Br2. 1 mole goes on the bottom. 79.9 times 2, 79.9 times 2 is 158.8 grams. No, it's not. I'm sorry. 159.8 grams. So I have 0.05 times 159.8 is 7.99 grams of Br2. So hopefully you feel pretty confident in the calculation of molarity. Now let's talk about molality problems. Principle doesn't change. Okay? You still do it the exact same way. So let's do one together, and then the other ones you can do by yourself and come back and double check my math to make sure you did it correctly also. So start by writing your formula. Again, it's moles, in this case it's NaOH, divided by kilograms of my solvent, and unless they tell you otherwise, the solvent will always be water. Plug in what you know. 10.7. My moles are going to go on the top because I know that my liters of water is 1.75. X is going to be 18 point, and we did this before, but I forgot, so I'm going to quick do the calculation again. 10.7 times 1.75, 18.725 moles. 1 mole goes on the bottom. 40.01 grams go on the top. And this comes out to be 749 grams of sodium hydroxide. Now notice that the numbers came out to be the exact same. Why? Because my kilograms and my total volume were the same. Ooh, this is not liters, this is kilograms. Okay, my kilograms and my total volume were the same. Now you say, wait a second, Mr. Siegel, you just changed the liters to kilograms. How could you possibly do that? Very, very important point right here is 1 gram of water is equal to 1 milliliter. Okay? This is important. Make sure you have this memorized. Okay? 1 gram of water is equal to 1 milliliter, which means that 1 kilogram is equal to 1 liter. Okay? So, anytime you see liters, and this is for water only. Anytime you see liters of water, know immediately that that is the kilograms of water, or milliliters of water is the grams of water. Okay? Now, if the total volume and the amount of water is the same, you'll see that you get the exact same information for molarity and molality. Let's solve a couple. Again, pause it real fast, and then come back after you're done to see how I solved it. Okay, it's a molality problem. So molality is equal to moles of chlorine, Cl2, over kilograms of water. 5,000 grams divided by 1,000 is 5 kilograms. They don't give me my moles, but I'm going to use that 16.1 grams of Cl2 to solve for grams. Notice it's diatomic, so 70.9 grams is the mass. I'm going to solve with my calculator. 16.1 divided by 70.9 is 0.227. That is my number of moles. Do quick the math. Divide 0.227 by 5 divided by 5 is 0.0454. Notice again, got to put the little m because you have to include your units. Okay? Okay, one last one. What is the, again, pause. Welcome back. Okay, what is the molality of a solution containing 125 grams of iodine and 750 grams of carbon tetrachloride? So, molality, moles, kilograms. Now, this one's a little bit different. Notice, no water. Okay, so I've got iodine and carbon tetrachloride. How do I decide which one is the solute and which one's the solvent? Simple. The bigger the mass, the more there is, the better chance it is of being the solvent. So since I have 125 grams of iodine and 750 grams of carbon tetrachloride, my carbon tetrachloride is going to be my solvent. Carbon tetrachloride, CCl4, iodine is of course diatomic. So now I can do my math. It says what's the molality, so I'm going to solve for molality. Divide by 1,000 to give me the kilograms of my carbon tetrachloride. The iodine, I have to solve for. This is math that I can't do in my head. Let's see. Iodine weighs 126 times 2 is 252. Let me double check that. Okay, so I'm going to quick do a mole conversion for my iodine. 1 mole on the top. Iodine weighs 126.9. I know, you're impressed. I knew that without looking it up. That's because I'm a chemistry guy. Okay, 253.8. 253.8 grams. Take 125 divided by second answer. 0.493 moles of iodine. That goes on the top of my calculation. Go back to that handy dandy calculator. Divided by 0.750. 0.657 is my molality. Notice again, I included the units. And that's how you solve molarity and molality problems.